Hello everyone, this is Dr. Ajay Kumar, Assistant Professor, School of Basic and Applied Sciences, Department of Chemistry, Maharaja Agrasen University. So my today's topic is basics of NMR spectroscopy. Okay, so what are something basics in NMR spectroscopy that I will discuss in today's lecture. Okay. So our NMR is comprises of mainly three words. That is your N, M and R, where your N stand for your nuclear and magnetic resonance. So what is the meaning of nuclear? Means something related to our nucleus. Means nucleus is the main that is responsible in NMR spectroscopy. Okay, and second one is your magnetic. Now what is magnetic? So magnetic means magnetism, how the magnetism is arises in our atom, that we are going to discuss here. And what is the resonance? So whenever we study spectroscopy, the resonance means something, means matching of something with something. And what is that something? That is the when we see the definition of spectroscopy, means spectroscopy means interaction of electromagnetic radiation with the matter. And what is that interaction? Okay, that interaction is particularly related to your resonance. Okay, so resonance basically in spectroscopy, definitely we are talking about our magnetic field, frequencies are there. So matching of frequency with matching of something frequency. What is that something that we are here going to discuss? So here we can see in the screen your background, that is your atoms. Okay, atom. Now the electrons in atom, nucleus. Okay. So next is our nucleus, that is shown in spherical shape, that is in red color. Okay, so when we zoom in our nucleus, we can see the two particles, protons and neutrons. So neutrons, what is the charge on neutrons, what is the charge on protons? Because this charge is extremely important for nucleus to be NMR active. Okay, whenever we have a nucleus that have magnetism, that is only that particular nucleus is active in NMR spectroscopy. So if we calculate the charge on our protons, we have protons and neutrons. Okay, now these protons and neutrons are consist of our subparticles, and those subparticles are quarks, and we know that on each quarks there is a charge. Okay, we have two types of quarks in our proton as well as in our neutrons. Okay, so +2/3 -1/3 on protons, and on neutron when we see the charge on neutron, that is neutral. If we sum up all these charges, in case of neutrons the net charge is 0, wherever in case of proton we can, when we sum up all these charges, the net charge is +1. Means that's why we dictate that our proton have +1 unit positive charge. Okay. So here we can see that the positive charge and the neutral charge on neutron as well as on our protons. Now we know that whenever a charged body or a charged particle is displaced or showing some movement, that will produce a magnetic field. Okay, whenever we have a charged body, it may be positively charged, it may be negatively charged. Whenever it move or show some motion, okay, it will generate our magnetic charge, or I can say magnetism. Okay, so we can conclude from this slide that our atoms behave as a teeny magnetic particles or a teeny magnet. Okay, so when we are talking about our magnetic field or magnetism, there is a dipole. Means if we talk about our magnetic moment or magnetism, if we have magnetic moment, means it has our two poles. One is our north pole and south pole. Okay, north pole and south pole. Okay, we can see here north pole, south pole. Okay, and I have already told that the atoms behave as a teeny magnet. Okay, now if we apply the magnetic field, what will happen to those teeny nuclei? Okay, what will happen to those teeny nuclei? Now if we have not external magnetic field, okay, these nuclei are randomly oriented, okay, means their direction in any, there may be oriented in any direction until unless we have applied some external magnetic field. Now what happen if we apply some external magnetic field? What will happen? Definitely our external magnetic field also has magnetic pole dipoles, means north to south or south to north, okay. Okay, so here what will happen when we apply the external magnetic field? Here we can see our nuclei arranges themselves according to the magnetic field, means north attract to our south pole and our south pole attract to north pole, okay. When such orientations are take place, we can say that our nuclei is in lower energy state. While it is not always possible, means we have, for example, we have 100 nuclei, all those arranges themselves in the direction of applied magnetic field. Some of them also repel, means some of them also in the opposite direction to the applied magnetic field, okay. So such nuclei, we can say that such nuclei are in high energy state, okay. So we have seen magnetism in our nuclear particles, or sorry, in our atoms. So what that particular things that make our nucleus magnetism, or how we can decide that our particular nucleus is NMR active or NMR inactive, okay. So if we can see in the slides, if we have even number of protons or even number of neutrons, the value of I here stand for your spin quantum number, okay. If I is 0, means our nuclei are NMR inactive, okay. Now if we have odd number of protons, odd number of neutrons, if we have even, odd even, we can see in the slides, we have we have some value of I, but when there is a odd number of protons, odd number of neutrons, or either both neutrons and protons are odd, okay. So in such cases we have some value of I, and what is I is our spin quantum number, means I here depict the amount of magnetic moment on that particular nuclei, okay. So we have some example. For example, if we have even number of proton, even number of neutrons, I is 0. For example, we have 12 6 and 16 oxygen, okay. So here we can see that if we have even number of protons and even number of neutrons, the I is 0, and we can say that our nucleus, our particular nucleus is NMR inactive. What does it means? What is actually meaning of this? So here we can say that whenever we have a pair number of neutrons or pair number of protons, means whenever we have something in pairs, okay, that arranges themselves also in pairs. So here we are talking about our atoms, okay. And what type of atom? Those are who have some magnetic moment on their self, okay. So if we have pair protons or neutron, what will happen? They will cancel their field, okay. They will cancel their field. For example, in the slide we can say that on the first particle, north pole on upside and south pole on downside, where next the south pole is upside and north pole is means downside. So what does it mean? It means it will cancel the field generated by each other, okay. So the net magnetic moment we have left is 0, okay. Means whenever we have pair number of protons or pair number of neutrons, the net magnetic moment is cancelled out, okay. And we can say that such nuclei are NMR inactive. Whenever we have odd number of neutrons, odd number of protons, means there is no pairing, okay. Means that have some amount of magnetic moment, and such nuclei can be assigned as NMR active, okay. So we have example. For example, hydrogen, number of neutrons 0, number of proton 1, means odd number of protons. And second one is your deuterium, number of neutron 1, number of proton also 1, so already odd number of protons. and we have C13, number of neutrons 6 and number of protons 7. Okay, so odd, the terms odd, that is more important for a nuclei to be NMR active with respect to your number of protons and with respect to number of neutrons. Okay. Okay. So now the thing is, why the nuclei with the spin quantum number I is equal to 0 is NMR inactive. Okay, I had already discussed, whenever protons or neutrons are in pair, they will cancel out each other field. Okay. Okay, thanks.